The Big Bang. Welcome to Brainghetti YouTube channel, where informative and interesting updates is what we do. Today, we are going to be addressing the Big Bang. But before we start, do you know Big Bang Theory explains how the universe developed from an original state of high density and temperature? Also, it is the established cosmological prototype illustrating the development of the visual universe from the initial known periods throughout its subsequent large-scale shape. Stick to the end to find out more. The model proposes an extensive solution for a wide spectrum of experimental indications, including the quantity of bright components, the cosmic microwave background, CMB radiation, and large-scale system. Crucially, the hypothesis is synonymous with Hubble Lemaître law, the observation that the farther away a universe is, the faster it is changing positions out from Earth, concluding this cosmic development backwards, in turn utilizing the known laws of physics. The hypothesis formulates an increasingly potent cosmos come before by a singularity in which vacuum and time lose meaning, generally called the Big Bang singularity. Thorough ratios of the development rate of the universe place the Big Bang singularity at an approximate 13.787 to 0.020 billion years ago, which has evaluated the age of the universe. After its first extension, an event that is by itself frequently named the Big Bang, the universe chilled satisfactorily to allow the construction of subatomic particles and later atoms. Huge clouds of these primordial elements, especially hydrogen, with some helium and lithium later, merged through gravity, constructing first stars and galaxies, the offspring of which are noticeable today. Moreover, these immature installation equipments, astronomers examine the gravitational consequences of an unspecified dark matter encompassing galaxies. Most of the gravitational capacity in the galaxy appears to be in this pattern, and the Big Bang theory and several observations imply that this extra gravitational ability is not established by baryonic matter, such as natural atoms. Ratios of the redshifts of supernovae imply that development of the universe is launching, an observation assigned to dark energy's reality. In 1927, an improving galaxy could be tracked back in moment to an originating solitary point, which is named the primeval atom. Edwin Hubble verified through analysis of galactic redshifts in 1929 that universes are indeed drifting separated. This is significant observational indication for an improving universe. For many decades, the scientific society was divided between advocates of the Big Bang and the rival steady-state prototype, which both requested bases for the experimental development. But the steady-state model specified a lasting cosmos in difference to the Big Bang's limited age. In 1964, the CMB was found, which encouraged many cosmologists that the steady-state hypothesis was fabricated, since, unlike the steady-state theory, the hot Big Bang indicated a consistent atmosphere radiation throughout the universe caused by the increased temperature and consistencies in the distant history. A wide span of practical information strongly supports the Big Bang, which is now practically universally acknowledged. The Big Bang theory gives an extensive basis for a wide range of observed events, including the quantities of the light components, the CMB, large-scale system, and Hubble's law. The theory is sure of on two major assumptions: the universality of real laws and the cosmological standard. The universality of real laws is one of the basic principles of the hypothesis of relativity. The cosmological notion states that on huge scales, the cosmos homogeneous and isotropic, arising the same in all paths regardless of location. These impressions were originally taken as postulates, but later actions were made to test each of them. For instance, the first hypothesis has been assessed by observations showing that biggest feasible deviation of the fine structure constant over much of the age of the cosmos is of order 10 to 5. Also, widespread relativity has passed tough examinations on the scale of the solar system and binary stars. The large-scale universe emerges isotropic as perceived from Earth. If it is indeed isotropic, the cosmological standard can be derived from the simpler Copernican principle, which states that there is no choice or special observer or vantage point. To this end, the cosmological principle has been verified to a level of 10 to 5 via awareness of the elements of the CMB. At the scale of the CMB horizon, the cosmos has been assessed to be homogeneous, with an upper edge on the order of 10% in homogeneity as of 1995. The growth of the universe was deduced from early 20th century astronomical attention and is a crucial component of the Big Bang theory. Mathematically, public relativity describes spacetime by a measure which determines the distanton that diverse nearby degrees. The degrees, which can be galaxies, stars, or other objects, are stipulated using a coordinate diagram or grid that is laid down all over spacetime. The cosmological law indicates that the metric should be homogeneous and isotropic on huge scales, which uniquely pinpoints the Friedmann, Lemaître, Robertson-Walker FLRW metric. This metric includes a scale component, which characterizes how the magnitude of the cosmos changes with time. This allows an effective choice of a coordinate strategy to be made, called co-moving coordinates. In this coordinate strategy, the grid expands along with the cosmos, and subjects that are walking only because of the growth of the universe remain at stabilized points on the grid. While their coordinate distance, co-moving distance, continues steady, the physical degree between two such co-moving points expands proportionally with the scale component of the universe. The Big Bang is not an eruption of matter moving outward to fill a vacant universe. Instead, expanse itself improves with time everywhere and boosts the biological distances between co-moving points. In other words, the Big Bang is not an explosion in space, but rather a development of space. Because the FLRW metric determines a uniform diffusion of mass and energy, it pertains to our cosmos only. On large scales, local engagements of matter, such as our galaxy, do not inevitably expand with the similar speed as the entire universe. A significant component of the Big Bang spacetime is the existence of element horizons. Since the universe has a limited age and light voyages at a finite momentum, there may be incidents in the past whose light has not yet had time to catch up with us. This places a limit or a past perimeter on the most several objects that can be examined. Conversely, because space is broadening and more cold objects are receding even more rapidly, light spewed by us today may never catch up to very isolated objects. This distinguishes a prospect horizon, which restricts the exhibitions in the future that we will be prepared to influence. The existence of either type of horizon is sure of on the details of the FLRW model that characterizes our galaxy. Our knowledge of the cosmos back to very first times indicates that there is a past horizon, though in process, our view is also restricted by the opacity of the universe at first times, so our view cannot expand further backward in time, though the horizon recedes in space. If the development of the universe proceeds to accelerate, there is a perspective horizon as well. Some procedures in the early universe happened too slowly, distinguished to the development rate of the universe, to reach approximate thermodynamic stability. Others were fast enough to attain thermalization. The parameter usually utilized to find out probably a procedure in the very early cosmos has attained thermal equilibrium is the probability between the rate of the technique, usually rate of collisions between particles, and the Hubble parameter. The bigger the ratio, the more time atoms had to thermalize before they were too far away from each other. As we've come to the end of this video, share your thoughts with us in the comment section. And don't forget to give this video a thumbs up and be sure to subscribe to get more of our video. See you in the next videos.